Hello fellow wizards, and welcome back to the Machine Learning at Microsoft YouTube channel. It's only been about a week since I saw you last time. Today is another one of those paper review calls, and we are now at number 17, and 17 is almost 20. Almost. When you get to triple digits on these things, people really know that you're taking it seriously. But it's a weekly opportunity for a data scientist or a software engineer or a researcher at Microsoft to take a paper from the literature about machine learning and to kind of tear it apart and to just help all of us take away useful, actionable lessons that we can use in our kind of day-to-day work. Now, we have Devon Hjelm today, and this is really, really exciting because normally we have engineers and data scientists that just work throughout Microsoft, and we don't have access to the primary authors of the research. We kind of read the papers ourselves, and we have a go at doing a kind of, a cack-handed interpretation of the paper. So today is really, really special because it's the first time that we've got a primary author from Microsoft Research to do one of these paper review calls. Devon did his PhD at the University of New Mexico, where he studied unsupervised representations of the brain using graphical models, which is really interesting. And he went on to do a postdoc under the tutelage of Yoshua Bengio. That's right, Yoshua Bengio. This is a man that requires no introduction whatsoever. And that work was kind of looking at unsupervised learning and adversarial learning and representation learning. At Microsoft, Devon's interests are about learning really powerful representations that can kind of help us in upstream tasks like natural language processing, reinforcement learning, and computer vision. Now, Devon published a paper with his colleagues this year, and the paper was called Learning Deep Representations Through Mutual Information Estimation and Maximization. And essentially what it is it's a way of looking at the mutual information of an input and an output of a model and maximizing it using stochastic gradient descent. And what this does is it allows you to learn really, really powerful unsupervised representations. And you can also train the model in a semi-supervised way. So you can ask questions of it in computer vision. You can say, does this patch belong in this image, yes or no? And this is kind of familiar to me, having read some natural language processing papers recently, because in natural language processing you see a similar kind of self-supervision. The skipgram model, for example, might model what's the next word in the sequence of words, and you can take a large corpus of text and you can kind of train this model, and you can get a really powerful language model and representations for words because you can kind of semi-supervise it on this large corpus of text. And it turns out you can do very, very similar things in computer vision and other domains as well. And there's a large similarity between the Deep Infomax paper and the continuous bag of words paper by Mikolov in 2013. So the mutual information between an input and an output is kind of related to the KL divergence. And it turns out that the first algorithm that used this, the Infomax principle, came from the ICA algorithm, the independent component analysis algorithm. And that does a very, very similar thing. It looks at the mutual information between the input and the output. So Devon talks about the evolution of this algorithm. So it started off as Deep Infomax, which was kind of looking at the mutual information between the input and the output of an image. And then they took it one step further and they kind of modeled the mutual information between the learned convolutional kernel values and the output, which gave it lots of interesting properties to kind of generalize different local patches over an input image. And then they came up with a really new interesting approach as well, which was using data augmentation and having two different types of input. They did a version using GANs. They also did a version on graph models. And then they did a spatial temporal version, which could be used for video and reinforcement learning. So there's an incredible evolution here of this algorithm. And they've just got some incredible results. The results are so exciting. And I'm not going to spoil the surprise. I'll let Devon present them. Unsupervised learning in general is really, really powerful because in the real world, not everything has annotations, not everything has labels. In fact, labels can be really, really difficult to come by, and having a powerful representation allows us to have a really generalizable understanding of what's going on in a domain. Remember to like, comment, and subscribe, and I'll see you back here soon.
Unfortunately, so
that's fine. To be honest, Bluetooth can be more trouble than it's worth. I've had so many problems with Bluetooth headsets on Windows laptops. Although you're using a Mac, which should be better.
I am.
Yeah, Bluetooth seems to work on the Mac.
It'll be.
Now, Devon recently published a paper with his colleagues called Learning Deep Representations by Mutual Information Estimation and Maximization. And it kind of describes an unsupervised algorithm for learning image embeddings by maximizing the mutual information between the input and the output of a neural network. And luckily, I don't need to explain anything about what mutual information is because Devon's going to go into great detail in today's call. But anyway, without any further ado, really excited to have you on, Devon. And I pass it over to you.
Okay, thanks for the kind introduction, Tim. So I'm going to switch to sharing my screen so I can get over to the slides. Okay, so thank you very much for being here today. I'm really excited to present not just one paper, but a bunch of different research on learning deep representations using neural networks by maximizing mutual information. So kind of what had happened is that this paper came out at some point, and because the principles were so readily applicable to other domains and other sorts of problems, it quickly generated a bunch of different papers as well. So I'm going to kind of try to give an overview over a bunch of papers that we produced recently, which basically follow Deep Infomax. Okay, so Deep Infomax is primarily interested in learning useful information, useful representations. And so by useful representations, we mean we have some sort of like, say, real world high dimensional input, and we want to extract information into a representation of some sort. And the usefulness is quantifiable in terms of its utility to one or a number of tasks. And
Devon, sorry to interrupt you. Could you share your screen?
Oh, ooh, I thought I did. Sorry. You failed the first test. Okay, I didn't click on the thing that said share.
Yeah, we've got you now. We've got you. Okay.
So Deep Infomax is primarily interested in learning useful representations. And by useful representations, what we mean is that we maybe have some high-dimensional real-world input from the real world. We want to extract information from this in the form of a representation, and the usefulness of this representation is quantifiable in terms of its utility for one or a number of tasks. And there's a number of tasks that people want to use these representations on. So generally, I would make the strong claim that the better types of representations are ones that have more utility. That is, that once you have this one representation that extracts in the real world, you can use it for a number of different tasks. And I would also sort of equate this idea of task generalization to understanding that in order to be able to generalize well to different tasks, you have to have a good understanding of the world. And this might be one way to kind of measure whether or not a model has understanding, is to evaluate it on many different tasks. So why is this important? Well, humans are really good at producing sort of like tasks that are difficult. Say we have sort of like a very abstract, complicated understanding of the world, and we have things that we want to be done in this world, and getting agents to understand what we need relies on them having that's a similar sort of complex understanding of the world. And sort of currently what the picture sort of looks like of this relationship between, say, an agent and a human being, more or less looks like the agent has a very limited understanding of the world. It has very limited representation. Some of them are hand built. And the human actually has to learn what sort of representation this agent is capable of performing under. So when I interact with Siri, for instance, on my phone, there's very specific types of commands that I can issue. And so I have to learn what sort of representation it can use to perform downstream tasks, and I have to alter my language in order for that to be possible. And we don't really want that. We want agents that are more or less on our level of understanding so that we can issue them arbitrary commands or give them arbitrary tasks in the world that are complex and that they're able to perform well. So arriving to understanding, I'm asserting that this isn't going to be a product of supervised learning, that is from models that are learned from annotation. And so one reason for this is that it's very difficult to describe for any particular data point of the real world from annotation exactly what's going on. So here's my attempt to describe through annotation what's exactly happening. And I challenge somebody to do better than this, but for a supervised learner, you might use this annotation and have the model try to predict these different annotations. And the hypothesis is if it's able to actually do this well, it accomplishes a good representation. But this was really difficult for me to do. And I would assert that this is probably not the best way to go about things, and certainly not the way that humans learn. So this is one among many reasons why we need unsupervised representation learning, is that the real world doesn't come with enough labels for us to faithfully train models to understand the world well. And even if we do have a set of what we consider good annotations, there's no guarantee that those annotations would tell the whole story that's necessary to perform well in the multitask setting. And in addition to this, there's just almost infinite amount of unannotated data available to us. So any models that we have that are trainable under unannotated data will have an advantage. Annotations also are problematic if there's things about the world that we don't know. I mean, I can only annotate things that I understand. And if I want to discover new things, well, there's no clear-cut way that annotations will yield this sort of discovery of this type of underlying structure in the data that I don't know about. And then finally, all this is sort of loosely related to sparse rewards in RL, where the reward signal is very, very distant from sort of the understanding that the model needs to understand to know in order to perform well in the environment. So this talk is going to cover basically Deep Infomax, but in kind of 4 different phases. One is Deep Infomax relies on mutual information estimation. And so I'm going to kind of cover very briefly a paper that we had from ICML, which estimates mutual information using neural networks. Then I'm going to cover Deep Infomax, and then the follow-up paper called Augmented Multiscale Deep Infomax, where we use principles of mutual information to learn supervised representations and images. Then I'm going to show that these ideas extend to other types of data sets like graphs in Deep Graph Infomax. And then finally, I'm going to talk about how we can also apply these principles in the RL setting, and how we can evaluate an agent's understanding to know whether or not it's actually learning something useful. So this is kind of my geocentric view of sort of unsupervised learning and what is called self-supervised learning, is that Deep Infomax lies in this is a type of unsupervised. More specifically, it's a type of self-supervised learning. So traditionally, a lot of representation learning focused on sort of generative models and these things on the outside of self-supervised learning, like GANs and VAEs and PCA and ICA. More recently, there's been a lot of attention to learn good representations using self-supervised learning, and I'll describe what that is next. So first of all, I'm going to make the argument that we don't need generation, or actually, if we're interested in learning useful representations, generation isn't what we should aim for. And so in principle, it's pretty easy to see why this is the case. Given any particular data set, there's a lot of instances of things or locations in, say, an image of things that are useful or interesting. And there's a lot of other stuff in images or even videos or whatever of stuff that we're not interested in, that's not useful. And the problem is that generative models want to produce every single pixel, say in this particular image, very faithfully in order to accomplish its objective. But we don't really want to penalize our model for being able to not generate or understand things that aren't useful, say the specific pattern of that couch or the pattern of the dog's fur. Or rather, we want to understand the situation and the main primary objects in the scene. So this is why we need self-supervised learning and rather over generative models to learn good representations. So self-supervision is a method for learning representations by training a model to answer procedurally generated questions about the data. And so I'll go over some examples so this is a little bit clearer about what exactly I mean here. But there's a lot of good things about this approach that I can cover now. So first is that if we have a good generator for these questions, we can potentially generate infinite amounts of annotation or self-annotation to train my model with. And I can also borrow a lot of tricks from supervised learning, such as classification or regression or whatever, without actually having to worry about labels provided by humans or whatever. This also allows me, if I pick the right type of questions, to focus on only the information that I need to perform well on tasks. And in other words, this is not going to be the pixels. And then if it's able to understand these questions well, the hypothesis is that the model has to have a very good fundamental understanding of the data. And so if it has this understanding, as I asserted before, it has this ability to be able to perform a number of different tasks in the world. And the only caveat to this whole approach is that you actually have to design the question generator. You have to design the thing that's asking questions about the data to the model for it to answer, which requires some understanding of the data, but I feel like that the trade-offs are well worth it. Okay, so here's some examples of self-supervision in the wild. So suppose I'm given a data set of video, and I procedurally generate a question by just, say, sampling a video and then randomly making the video forward or backward. And I ask a model, can you tell whether or not this video is going forward or backward? And performing this well requires an understanding about physics or like the directionality of time. Another question that can be posed in images, if I'm giving a bunch of images and I say I produce a question by randomly selecting patches, and I ask the model, can you tell whether or not these two patches go together or whether they're patches that come from two different images? And in order to understand this, you might have to understand things about objects on a larger scale than you would, in order to be able to understand this well. In addition, a related question is if I'm given a bunch of different patches, so I can procedurally generate like a bunch of different patches of images and a bunch of different queries, and I ask, where does this patch go? In order to understand this, I have to understand the structure of the object as well. And then another one is if I have different sentences, and I can simply ask, which of these sentences follows the other, and if I am able to answer this question well, or rather if the model is able to answer this question well, it has an understanding of, say, topics or meaning or semantics or whatever. Okay, so our take on self-supervision relies on mutual information, and it's worth just briefly covering what that exactly is. So the mutual information is defined as the Kale divergence between the joint distribution of two variables and their product of marginals. And so this is a useful quantity when we're talking about representation learning, is that we have this process in which we're trying to extract information. And it would be useful if we had some sort of measure for mutual information so we could tell how good our representation is, and even better, that we could implement learning in some way such that this mutual information is increased. And this is known as the Infomax principle, which is a cornerstone of the ICA algorithm. Now, our take in our methods are going to be slightly different in that we're going to be maximizing the mutual information between partial observations or views of the data, and these are going to be performed in the representation space. And so essentially, this comes down to asking questions about the data at the representation or feature level. That is to do self-supervision at the feature level of representations that represent partial views of the data. But before we can start talking about actually maximizing mutual information, we have to actually address the problem that mutual information is very difficult to compute, especially in the continuous and high dimensional setting. So I'm going to talk about our paper very briefly from ICML last year called Mutual Information Neural Estimation, where we introduce a neural network which gives you a mutual information estimator. This neural network takes in two variables, x and y, and outputs a real number. And given this neural network, there is actually a lower bound to the mutual information, which looks like that term near the bottom there. And so in order to maximize mutual information, it's just a matter of maximizing, or in order to estimate mutual information, it's just a matter of maximizing that term on the right-hand side of that equation. And so I can rely on neural network optimization, just maximizing that term, and stochastic gradient descent training this neural network omega with parameters omega. So rather than go through the simpler empirical results, I'm going to show you how this method was actually used to alleviate mode dropping in GANs. And mode dropping in GANs is this phenomena where sort of the GAN is only producing some of the modes of the data. And so the idea behind using mutual information neural estimation to help this is that if we have this estimator, we can actually use it to potentially maximize the mutual information between the input of the GAN, which is the noise, and its output to alleviate mode dropping. And this is kind of how it works. So I'm going to assume that there's some knowledge of GANs here. So basically you have some input noise, say produced from a Gaussian prior or something like that. You have a parametric model which transforms this noise into the space of the target distribution that you're interested in. And so in this case, let's say I'm training this model to generate images from noise, images of well-known deep learning scientists such as Yoshua and Bengio. So this is like, it looks like a really, really awesome model. Like it's producing these really great images, but unfortunately it's exhibiting mode dropping. It's only producing images of Yoshua Bengio, which isn't good. I wanted a good representative distribution of well-known deep learning scientists outside of Yoshua Bengio. And so the way that GANs work is that it introduces another parametric model, a deep network called a discriminator, and this thing tries to determine whether or not this image is real or not. And what we do in order to alleviate mode dropping in this sense is to use our neural network estimator for mutual information between the input and the output of the GAN, of the generator. And given that we have this estimator, we can actually use this estimator to maximize the mutual information between the input and the output of the GAN, and thus alleviate mode dropping and produce other, in this case, other images of famous deep learning scientists such as Jan LeCun. So here are some examples of this working. On the top, we have the common spiral data set where the ground truth samples are in blue and the samples are in orange. In the bottom, I have the stacked MNIST data set, which is basically sampled like MNIST, except for you have three color channels, and each of these color channels you randomly sample a sample from the MNIST data set. So you could have things like in stacks 9, 2, 1 in different channels, or 4, 3, 7, or whatever. So instead of 10 different modes, this actually has 10 times 10 times 10 modes, one for every channel, so 1,000 modes, and it's kind of like a demonstration of mode dropping. And so we approach this problem in these two data sets. So here's an example of mode dropping that happens in normal GANs. For instance, in the MNIST, stacked MNIST, it's producing a lot of things that looks very, very similar and not indicative of the ground truth. But when we introduce the mutual information neural estimator and use this to maximize mutual information with, again, the mode dropping disappears, and it's able to actually find all 1,000 modes of the stacked emptiness data set. Okay, so now that I have that set up, I'm going to go on to talk about Deep Infomax and using these mutual information estimators to maximize the mutual information between an input and a high-level representation, in this case with images. So at a very high level, if you just kind of naively think that you can just apply mine, it would kind of go like this. You would take your input, you would have a parametric neural network encoder, which would encode it into a representation Y, and you'd plug the input and output into your mutual information estimator. And because this thing's a lower bound, you can just maximize this estimate both for the mutual information estimator and the encoder simultaneously. But unfortunately, this won't work very well, and I can show you why. So it's related to that previous slide. There's a lot of relevant things in an image or data that I'm interested in. But there's a lot of other irrelevant information that I'm not interested in. And the problem is that if I'm just going to maximize mutual information with the representation and input, there isn't sort of like any bias for the model to learn anything that I'd consider useful. And I think it's actually a little bit worse than that. There's sort of bias to find a lot of different information that's unrelated. So for instance, suppose if I'm doing stochastic gradient ascent and I'm trying to learn good representations for this particular image here, suppose I first pick up some cat eye sort of information from that center green patch there. And then the model wants to say, okay, well, what sort of information can I encode next, which will increase the mutual information between the input and the representation? Well, it's probably not the cat locations, because it has already encoded cat information. So it's probably going to be something like, say, like the background, like having to do with the tree or sort of the pattern. And so there's actually a very heavy bias for this model to learn noisy stuff if you just try to maximize mutual information. So our hypothesis, what's that? Was that a question? Oh, okay. Sorry, I thought I heard a question. So what we want actually is to learn the shared information across all these different locations, say the cat information as is present across the image. So how do we do this? Well, we remember that we're working with convolutional neural networks. And at some level, we have a set of local feature vectors at a convolutional layer, which correspond to patches of the input. That's the C super I's, where I is the index indicating a particular location. And then at some point, we summarize this into a global representation Y, which represents the information or the representation for the whole input. And instead of maximizing the mutual information between the full input and the full representation, we've maximized the mutual information between a patch level representation at the conv layer and the high level representation. And this is something that we call self-prediction, because this global representation is a function of all these different patches. And we estimate and maximize mutual information across all these locations simultaneously. So kind of at a high level, why this actually works is related to that if I have shared information across the input, if I maximize the average mutual information across all locations, it's more beneficial for me to capture something shared than it is for something distinct. So for instance, if I encode the cat information, the sum of all the different mutual informations of all those cat patches is higher than if I try to capture something like tan or window or something like that, something that's less prevalent in the image. So this is a way to encourage the model to learn shared information across all the locations.
Devon, just a quick question. Are there any computational advantages to using this mutual information between the convolutional, the kind of the patch and the output? I mean, for example, is the model more parameter efficient, or does it converge better?
Well, so like one strong advantage is that so you can kind of view all these these local feature representations at the conv layer as sort of like a specific view of the data, because those represent, so they have like a limited receptive field. So they represent a patch of the input. And so this means that if I wanted to do this sort of prediction between different views of the data as represented by patches, it's naturally represented already in the convolutional neural network. I have all these different views that are already in the different layers, and I don't have to do something like crop in order to produce a different view, which is pretty common in other self-supervised methods. Right. So you can imagine, like, I could get something similar to the C sub I by just taking a crop of the image and producing a single representation, and then I produce a global representation by taking the full image and producing another representation, and then trying to maximize the mutual information between these two. But this would be really inefficient because I have to do all this different sorts of cropping and I have to sample from it. But I can naturally take advantage of the convolutional structure to get these views almost for free, just by the fact that I'm using this particular well-used structure for processing the image. Does that make sense?
Yeah, it does. Yeah, really interesting.
Okay, so I'm going to step back and talk a little bit more about actually estimating mutual information. And so basically, these estimators are essentially just classifiers. So suppose I'm given this setting where I'm trying to encode the input. So I have an image X and a representation Y, and my mutual information estimator wants to classify these, say, as a positive sample. So this is binary classification. Now, the other side of mutual information is the product of marginals. And so we can just sample from the product of marginals by, say, sampling images and representations that they don't necessarily go with. For instance, taking the dog representation, a representation for a particular instance of a dog and pairing it with some other instance of some other image. It could be a different dog or a cat. And we want to classify this as a negative example. And so mutual information estimation essentially comes down to finding the optimal decision boundary between these two sets. So now there's a lot of different options once you accept that this is just a classifier, because this classifier is just an estimator for the log ratio between the joint and the product marginals. And so, and this whole thing kind of works similarly to GANs, in that GANs are also estimators for log ratios, but the generator is acting in the opposite direction of the discriminators, trying to be adversarial. In this case, with the encoder, they're all both trying to work together. So the encoder, the mutual information estimator, is trying to be a really good classifier, and the encoder is trying to make the job easier for the classifier. It's trying to make it easier to separate between the joint and the product of marginals. And so once you accept that this is a classifier, you have a bunch of different options. So in our paper, we introduced just using plain old binary cross entropy, rather than that mutual information found in the MIND paper, which works really well. It's really stable, and we know neural network optimization is really efficient under binary cross entropy. There's also another related a related method called noise contrastive estimation, which was used in the contrastive predictive coding paper, which is basically amounts to a multi-class classifier, but it's essentially doing the same thing. It's still estimating and maximizing mutual information. So once we have a good representation, how do we actually evaluate it? And this is where things get a little bit hard. So in our work, we're working mostly with image data sets. And so naturally, we have a bunch of these annotations laying around, the class labels. And so we can, instead of actually training the model on these class labels, we can evaluate the representation based on its ability to encode class level representations or class related information by simply keeping the encoder fixed, not doing any training at the lower levels or anything like that, just taking the representation and building a very small classifier on top of it to see if you can actually classify well. And the idea is, if you can, that means that there's class level information in that representation. That representation has at least information about the classes. And you can perform this probe using a number of different types of classifiers, either linear or nonlinear classifiers, and you could do it at the global level, or you could even do it at the local level and see if you can do slightly better. In addition to this, we did a few other evaluation techniques. One was we just evaluated it using mine. We trained mine on top of the encoder to see how much information was in the representation. We introduced another measure, which we call the neural dependency measure, but it essentially comes down to measuring the total correlation in the feature representation to see, if you're interested in stuff like disentanglement, to see how much entanglement is in that representation. And then finally, you could also train another decoder on top of your representation to try to evaluate how much say structural information, high-level structural information is in the representation based on the ability to be able to just reconstruct the original image given the representation, once again, without any back propagation through the encoder itself. And this is kind of like the opposite end of the spectrum of classification. On one end, you're just trying to evaluate whether or not a single bit is, or one of among a small number of bits is in the representation. And the other, you're trying to figure out if you can actually produce everything up to pixel level detail of the representation from the representation of the input. So I'm going to present quite briefly the results on classification. So this is building a single layer neural network on top of the representation, seeing if you can actually classify given that representation, not back propagating through the encoder. And so with a fixed setting where there's no data augmentation, just using some standard either AlexNet or GAN-like encoders, we found that Deep Infomax far outperformed any of the other unsupervised methods that we compared to, especially the generative models. And it actually, in this particular setting, performed quite well compared to supervised learning on a number of different tasks. Now, the big caveat is, though, of course, you can find much, much better results on all these data sets for fully supervised if you use data augmentation, if you use the latest architectures. But we wanted to kind of keep everything very level, and it was very promising that it was able to perform very well in this setting. So what Deep Infomax is basically doing is it's maximizing mutual information between a global representation, which is a full view of the input, and a local representation, which is like a partial patchwise view of the input. And so there are a lot of different methods that do sort of similar sort of things. One is called contrastive predictive coding. So contrastive predictive coding kind of builds like a aggregate view of the whole input using an autoregressive model, and that's the green part above. Here, I'll go through that animation again. And then it predicts or maximizes the mutual information between that aggregate and sort of like a set of downstream patches that aren't seen in the aggregate. So it's doing a purely autoaggressive sort of task, such that the predictor and the predicted are coming from two different things. And this approach can make things a little bit harder for the encoder. It's kind of like more or less asking a more difficult question. And this is actually very easy to implement in the case of Deep Infomax by just incorporating in inclusions. And that is like I include part of the image, and so I get a partial view of the input. And then, so I have a global feature vector that represents only that partial view, and then I ask it to maximize the mutual information between that partial view and the local representations, the patch level representations of a full view. And this is a way to incorporate in autoaggression. Now, because this is a convolutional neural network, we can actually do this quite easily by leveraging the structure. And it kind of goes like this. So you have a single, you have your local representations, and then you can incorporate another convolutional layer on top of this set of local representations to get a set of, say, more global local representations. And you maximize the mutual information between these, say, more global and more local representations simultaneously. And this essentially just comes down to maximizing mutual information between two different views, one of them smaller than the other. So say bigger patches versus smaller patches. And this approach can't help in the same, yeah.
Sorry if this is a silly question, but the feature vectors that we're learning here, they still seem to be in the spatial domain. But I suppose if you think about it, in any convolutional encoder, at some point we sufficiently transform it nearly out of the spatial domain, and then we flatten the feature vectors. But is it particularly relevant or important that there's still some spatial information in the resulting feature vectors?
Yeah, absolutely. So, and the thing that Deep Infomax is doing right now is it's leveraging the architecture to pose these different questions about the data within by actually leveraging the fact that you believe that a particular location on a convolutional layer corresponds to something local, right? Now, if, for instance, I use a very, very large ResNet architecture on the full image, I quickly have these receptive fields that cover the whole image. So if I try to say, like, take this local feature vector at this level and try to predict this other feature vector at this other level, if they already cover the whole image, that's just like asking a question about itself, and it can find these very trivial solutions. It doesn't have to have a very good understanding of the data in order to do that. So there is a very important aspect of this, is that the questions have to be relatable to a partial view of the data. And if you're going to leverage the local structure, the structure of the convolutional network like this, you have to be careful about the receptive fields.
Cool. Thanks a lot.
Make sense? Okay.
Yeah.
So here's some results, the same sort of benchmark, comparing to contrasted predictive coding, where we're comparing either using the single global vector, which represents the whole view, or the multi-global vector, where you have all these different larger but not still whole views of the data in the mutual information objective. And we found that especially with larger data sets, this could help substantially. Just a couple other tasks or questions that we asked relatable to self-supervised learning in our work. One is that we introduced two different types of coordinate prediction. For instance, given a global representation and a local representation, can I predict the location? Or given a global representation and two different local representations, can I predict their relative location? And so this kind of requires the representation to learn something about localization. And so you can imagine that this is perhaps like an important aspect of a good understanding of a model. And so we found that introducing this sort of task can help in a lot of cases and improves results. Now, the paper that I just talked about was our Deep Infomax. This is our follow-up paper by Phil Bachman and us, where we actually extend upon these ideas by incorporating in data augmentation and introducing a lot of different questions about the data in many different objectives given the same model. And so basically the way that we augment Deep Infomax is that instead of just taking the full image and processing it in the way that I described before, you take two different views of the image by just using random data augmentation, say by randomly cropping the image, doing color jitter, other sorts of data augmentation. So you produce these two different views and use this as two different inputs to the encoder. And you pass this through the encoder in two different passes. And the basic idea is that you perform Deep Infomax across these two different views. And then you can go one step further and do this across many different levels. And basically, we're simultaneously taking advantage of the data augmentation to produce lots of different views, and the network architecture to also produce different views. Because as I mentioned before, all these different feature vectors at all these different locations represent different views of the data. And so we can simultaneously answer tons of different questions by leveraging these different ways of procedurally generating questions about the data and asking the model to answer it. And so in doing this, the results are quite impressive. And we accomplished state-of-the-art across numerous benchmarks for unsupervised learning, and even surpassed supervised learning in some benchmarks. So for CIFAR 10 and CIFAR 100, we far outstripped any of the unsupervised state-of-the-art using this method. For STL 10, we have the absolute state-of-the-art by a very large margin. of 93% on SDL10. And then finally, we are about like 7 or 8% above any other competitors, or I guess, 7% above any competitors using for unsupervised state-of-the-art for ImageNet. So these numbers are pretty impressive. They're that 68.1% is far above the original AlexNet score for ImageNet as well. Okay, so I'm going to talk about, how are we on time, by the way? Are we good?
We've got 20 minutes.
20 minutes, okay. Are there any more questions as I go on to graphs?
One quick question is, can people, are there any implementations online so people can make use of this algorithm?
Yeah, absolutely. So if you look up Deep Infomax on GitHub or the related paper on GitHub, I'll have the titles of the papers at the end of the talk. You'll find them very quickly. So there's implementations for actually almost all of these, except for the Atari one, I think is still pending.
One other question is, this whole thing about self-supervision seems to be something that we've seen a lot in the language processing world, because I don't know, when we build a simple language model, we might predict what the next word in a sentence is, or whether the sentence belongs after this sentence, or predict some masked words in the next sentence. And I'd never really thought about this applied in the vision world before. You were saying, do these patches belong in the same image? And it seems to be something that I've not really seen exploited before. And I wondered whether people had used this prism of mutual information in the natural language processing world as well.
So you're absolutely right about the connection to language, and actually there's a number of models that are relatable to mutual information as well. Even the original Mikolov paper from 2013 has an objective that's very close to ours that is definitely relatable to mutual information as well. So unsupervised representation learning, or in NLP, is very reliant on self-supervision.
Right, and Mikolov's paper from 2013 was the skipgram model. I think it was, the model he called it in there is something else, but I can't remember. Oh, the continuous flag of words.
It's the one where they have they have this dot product of context representation, query word representation, and then they have a bunch of negative examples that come from somewhere else. Yeah, that's correct. Yeah, so that's very close to what we're doing here. It's very close to the it's very close to the Jensen-Shannon version that we have. And then some other works in NLP used essentially what's the info NC, or the multi-class classifier version in NLP, and those can be found pretty readily.
That's fascinating, because people use the skipgram model absolutely everywhere in language processing to generate word embeddings. And as you say, it's computed by going through a corpus of text and just saying, does this word belong in the context of this other word? And you can produce these incredible word embeddings. And presumably you're saying conceptually we're doing something quite similar, but we're asking a different question in the vision world.
Yeah, I mean, there's a lot of different models that are doing similar sorts of self-supervision. I mean, even there's models that do self-supervision using the representations and having some sort of metric for whether or not something should be together or not. Whether they're using, some sort of L2 loss or a multi-class or a classifier sort of framework. And then there's a whole different set of them that use maximum likelihood estimation, like the BERT model, where they actually try to model the words given the masked out version of the sentence, right? And that's also a version of sort of self-supervision, but it's just a different sort of objective function. Directly modeling the probability of that word versus try to build sort of a metric space in order to try to answer these questions on.
Fascinating.
Yeah. Okay. So really quickly after the Deep Infomax paper came out, a student of mine, Petar Velikovic, came out with, he followed up on Deep Infomax to produce a version that works on graphs. And it more or less works like this. So you might have like an input graph, and you're going to use some graph convolutions to encode this into a set of node representations. Yeah. Oh, someone's mic is on, I think. Was that a question or was that a mic fail? I guess it's a mic fail. So you have an input graph, you have some graph convolutions, and you have a set of node representations that are the output of the graph the GCN neural network. And so you can think of these node representations as sort of the local representations in the convolutional neural network, kind of analogous to that. And you can get a summary very simply from these node representations by just taking a simple sum. And this would be the global representation as in Deep Infomax. And so what we do in the graph case in order to produce negative samples is we just produce a corruption function. And this kind of like shifts the the node representations around. And then you encode these, and then you just simply ask the discriminator, the mutual information estimator, to distinguish between summaries that come from the true node or neighborhood representations, and the fake ones that come from the corrupted graph. And so we first tried this in the transductive setting, and we were able to produce very, very good results just by training a very simple linear classifier on top of these representations.
Sorry, Devon, could you define transductive? Does that mean particular to particular?
That means like when the test, that you have the test examples available during training.
Right.
Yeah. There's that particular setting. So we also applied this to very, very large graphs such as Reddit. And because Reddit graphs are so huge, we had to do a different sort of sampling scheme in order to actually train this thing. And so what we do is we sample a bunch of different subgraphs, and these are local representations from these different subgraphs. Just by using GCNs on these local subgraphs, and then we summarize by just taking the average or sum across all these different local subgraphs, and then negative examples are produced by just using different subgraphs that aren't part of this summarization. And on this, we're able to do quite well on Reddit. We actually approach supervised learning, which is pretty remarkable on this very high dimensional data set. And then on the PPI data set, which is like a protein related one, we're able to do much better than other competing like unsupervised models, but not quite as good as unsupervised or supervised, because in PPI, there's a lot of zeroed out data that corresponds to just data that's not present or dropped out. I also wanted to mention that was kind of interesting that we found out about our paper is that the inductive bias from GCNs is quite strong. So the random init GCN both here and here are both when you don't train a GCN at all and you just try to evaluate the representation just by using a linear classifier on top. And actually this method does as well as, or sometimes much better than, some of the unsupervised methods that were used in the wild at the time. Which was pretty remarkable. So it turned out that our baseline that we had to beat was the random init in a lot of cases rather than the other unsupervised methods. Okay, so I'm going to have the one last section. Is there any other questions before I go on to Atari? Okay, so finally I'm going to talk about applying these ideas to the setting of RL. And also trying to actually evaluate the understanding of these representations a little bit better than just using these single annotation classifiers. So good unsupervised representations in RL would be especially helpful, especially since we have a strong need for sample efficiency, especially when you have sparse reward environments. And we can't really rely that well on human annotation or RL environments because this is particularly expensive. But the problem is that among unsupervised methods, generative models don't particularly do very well, is because they have to be able to model things in time. And most video generation sort of methods are very poor at generating sequences of images. And then finally, even if you do have a method for training a model in an unsupervised way, it's hard to evaluate whether or not your model is actually learning something useful. You have to kind of like wait for these things to train for a while, evaluate the return, and then decide from that whether or not it's doing something useful or not. And it would be really nice if there was a way to actually evaluate the model's underlying understanding to see if it's learning something useful that you think is necessary for it to perform well. So in Atari, thankfully, we have access to the RAM. And so given that we have access to the RAM, this means that we have sort of the ground truth or underlying factors of the actual state space. So for instance, in Montezuma's Revenge, we know the location of the agent or a bunch of different enemies or other objects. We know the score, the number of lives, etc. Or in Pac-Man, we know a similar source of information about the location of Pac-Man and all the other enemies, how many dots have been eaten, and what the score is. And so what we're going to do is we're going to actually use this underlying ground truth information that we have access to as an evaluator for the representation. And that is that we're making the hypothesis that a good representation has information about these ground truth factors. A good representation should know where the location of the enemy or the agent is, or at least this information should be extractable. So we take our representation and we just train these different linear probe classifiers without actually backpropagating through the representation like we did in the classification case to see if we can classify well on these ground truth factors given the representation. In addition to this, we introduced another version of Deep Infomax called spatio-temporal Deep Infomax, which operates both on the spatial and temporal domains simultaneously. That is, it tries to maximize mutual information between global and local representations and future local representations. And in this, it's trying to find not just spatially consistent information, but spatially and temporally consistent information. And we evaluate Deep Infomax, spatio-temporal Deep Infomax, along with a number of other methods for learning unsupervised representations in Atari for a number of different games. And this is all the F1 score for all these different games, for all these different classifiers. And we found that spatio-temporal Deep Infomax routinely outperformed all the different methods, including the contrasted predictive coding. And especially what's notable is that pixel prediction, which is just a generation of future frames, doesn't do particularly well compared to the self-supervised models like CPC and STDIM.
Devon, a quick question. The spatial temporal Deep Infomax, is that essentially a similar concept but using a 3D CNN over frames in time?
Let's see, not particularly.
Okay, I didn't quite understand this diagram then.
This diagram, so yeah, each of these different frames are processed independently of each other. So just using a standard 2D convolutional neural network. But you're kind of viewing these different representations, these local and global representations at different views of the data, both in different locations and different time points. Right. So, and then you're just requiring that the representations carry similar information across these different dimensions, both space and time.
Okay.
Yeah. So those are the results for just some sample of different games. And on average, the STDIM does much better than the other models that we compared to. And then in addition, this kind of gives us an idea about the agent's understanding, because these different questions, say the location of a particular enemy, the location of an object, are relatable to different categories of understanding, say localization or understanding the score or where the agent is or where the objects are, etc. And we found across all these different categories that STDIM did quite well. But this sort of framework of having an evaluation metric on top of representations can tell you, whether or not your model's understanding certain things better than other things, and maybe can guide researchers to have better design of their agents in order to accomplish better scores. Say like small localization. Okay, so there's a bunch of small objects in the scene, and the agent keeps on running into it because it doesn't understand that they're there. So its small localization score is really low, and so you can figure out, how do I boost that small localization for the benefit of the agent understanding that those small objects that are there, so that it can avoid it or get it, depending on whether or not it's good or bad. Okay, so that's it. So there's some code up for both Deep Infomax and Deep Graph Infomax. There's also code available for the Phil Bachman paper, Learning Representations by Maximizing Mutual Information Across Views. And then the unsupervised state representation learning in Atari, particularly the RE benchmarking code will be up fairly soon, so people can actually use that to evaluate the representations. And thank you very much.
Devon, thank you so much. This has been absolutely fantastic. We've got a few minutes, so if anyone would like to ask Devon a question, now's the time.
Sure. What's the future directions that you guys are going to be working on with this?
So there's a lot of different potential directions. So we've only kind of touched the surface on what it means to maximize mutual information between views. So our views, for instance, in the image case, were taken from just applying data augmentation that was borrowed from the CV community. But the natural world provides multiple very interesting views of objects and other sorts of things that we want to encode information about. And so a very natural thing is to move into the video domain without necessarily relying on data augmentation, but sort of the natural data augmentation that's present in the world, say the fact that ambient lighting has variation, or you experience different, like say, shades or orientation of objects in the world. And to see if sort of natural object representations emerge just by the fact that you're seeing things under different conditions, and you're trying to learn a representation that's finding consistent things under those conditions.
Thank you.
Yeah.
If you did build a sort of Deep Infomax on, using video as an input, would it generalize to static images again?
I think that's a good question. I think yes. I mean, static images are derivable from video, right? So the idea that we can actually identify something in a frame, I think, comes from our experience from video, or like, temporarily not expressed, but things that exist in the world temporally that we're experiencing. So
I suppose I just mean that the encoder would have multiple frames as an input, but I suppose you could just repeat the frame multiple times.
Oh, I see. Yeah, well, that's an architectural detail. I mean, if you have a model that takes in like 3D input as part of its architecture, like the 3D convolutional models or some other variations on that's used in video, then yeah, you might have to do something like actually present it as a video by repeating frames. But I don't know if anybody's actually done something like that. I'm sure they have.
Brilliant. Okay, well, I'm going to wrap the call up. Devon, thank you so much. Next week, we've got Miguel Fierro on Monday. He's in the Azure Cat team, and he's been working on a recommendation library, which is on GitHub, which has got all of the current best-of-breed recommendation algorithms. So he's going to talk through that. And then we've got Jing Dong from Microsoft Research in Beijing, who's going to talk through this HRNet paper, which is a vision paper, which kind of can be used for lots of upstream tasks like pose detection and semantic segmentation, and is currently the state of the art for many of those upstream tasks. So thank you very much indeed. Thanks again to Devon, and we'll see you all next week.
Thank you.
Say hi to William Buchwalter out there.
Oh yeah, for sure. Okay. Are we off or are we still recording?
I shall stop recording. But yeah, that's a wrap.
Okay. Thank you. I'll sign off.
Yeah, Devon, thank you